Today we are walking through the paper titled Agentic Harness Observability-Driven Automatic Evolution of Coding Agent Harnesses.
What problem does this paper start from?
The paper starts from a very practical point. Coding agents are not just a model plus a prompt. Their performance depends on a harness, meaning the tools, middleware, memory, skills, subordinate settings, and execution rules that shape how the model acts.
So the gap is not only model quality. What was hard about improving the harness itself?
Earlier optimization methods usually changed one surface, often the system prompt. This paper argues that a real harness is messier. There are many editable components. Each rollout produces huge trajectories. And after an edit, it is hard to tell which file actually caused a fix or a regression.
What does the paper propose instead?
It proposes Agentic Harness Engineering, or AHE. The base model stays fixed. Another agent edits only explicit harness files, runs the coding agent again, and uses the next round of task outcomes to keep or revert those edits. The key idea is observability. Component observability makes the editable harness pieces visible as files. Experience observability compresses what trajectories into evidence an agent can read. Decision observability records what an edit is expected to fix a risk before the next evaluation checks it.
Can we see how those three pieces fit together?
This pipeline diagram is the method in one view. The coding agent runs tasks using the current harness. The debugger turns the resulting trajectories into structured evidence. Then the evolve agent edits harness files and writes a manifest that predicts which tasks should improve and which may regress.
What keeps the evolve agent from taking shortcuts, like changing the evaluator or switching the model?
The paper puts the editable harness in a controlled workspace. Runs, tracing, verification, and model configuration are read-only, and the seed prompt cannot be deleted. That means a measured gain must come from harness edits, not from moving the goalpost. The harness substrate is called NextAU. It exposes 7 component types as separate files: system prompt, tool description, tool implementation, middleware, skills, subordinate configuration, and long-term memory.
Why does separating the components matter for the optimizer?
Because the action space becomes inspectable. If a failure pattern points to missing tool behavior, the evolve agent can edit a tool. If the issue is step-to-step state or safety around execution, it can edit middleware. The change is easier to review and easier to roll back. The first metric on the board is pass at 1. It averages task success over the benchmark tasks and repeated rollouts. Here, each result is 1 if the trial passes and 0 if it fails.
So pass at 1 measures success.
The second metric is successes per million tokens. It keeps accuracy and cost tied together by dividing pass at 1 by the mean token use per trial, scaled to 1 million tokens.
What happens when they run the full AHE loop?
On terminal bench 2, 10 AHE iterations raise pass at 1 from 16.7% to 7.0%. That beats the human design Codex CLI harness at 71.9%, and also beats the self-evolving baselines A, C, E, and TFGRPO that start from the same seed.
Why is the shared base model important for that comparison?
All 3 roles use the same base model in the main experiment: the code agent, the debugger, and the evolve agent. So the comparison is not saying that a stronger analyzer or editor won. It isolates the improvement to the harness changes produced by the loop.
Does the evolved harness only work on the benchmark it was trained on?
The authors test that by freezing the AHE workspace and reusing it without more evolution. On SWE bench verified, the frozen harness has the best aggregate success while using 12% fewer tokens than the seed. AC and TFGRPO do worse than the seed there while spending more tokens. They also test transfer across base models on terminal bench 2. The same AHE harness is paired against the original seed for each model family, without rerunning evolution.
What pattern should I take from the cross-model plot?
Every tested model shows a positive pass at 1 gain, ranging from 2.3 to 10.1 percentage points. The size is not monotonic inside one model family, because the evolved step budget and timeout were tuned around one operating point, but the direction stays positive.
Which harness spots carry the improvement?
The ablation points away from the system prompt. Swapping in only long-term memory, only tools, or only middleware improves over the seed. But swapping in only the evolved system prompt is the one single component change that regresses.
How do they check whether the edit predictions were meaningful?
Each round, the evolve agent predicts which tasks the next harness should fix and which tasks might regress. The paper compares those predictions with the next round's actual outcomes across 89 tasks, measuring precision and recall separately for fixes and regressions.
Were those predictions actually better than guessing?
For fixes, yes. The reported fix precision is 33.7% and fix recall is 51.4%, roughly 5 times the random baselines of 6.5% and 10.6%. Regression prediction is weaker, which the authors treat as an important remaining limitation.
What should we keep in mind about the limits of this result?
The evidence is promising, but the scope is still controlled. Evolution happens on terminal bench 2. Transfer is checked on SWE bench verified in several model families and broader programming languages. Repository scale deployments and human-in-the-loop workflows remain untested. The takeaway is that AH treats harness engineering as an observable, testable loop. It does not just ask an agent to rewrite a prompt. It makes components, evidence, and edit decisions visible enough that another agent can improve the harness and be checked afterward. That wraps up this paper walkthrough.